So in our last example here, we've got y of x is the sum from n equals 0 of a sub n x to the n. So we're being given a generic power series. And we want to find power series expressions for y prime of x and y double prime of x. And then we're going to shift the indices of summation so that they start at n equals 0. So this is actually an example that is designed to warm you up for using power series to solve differential equations, which is what we're going to be using in the next lecture. So I really encourage you to focus on how this example works, because essentially the start of every problem in the next lecture is going to be exactly what we're doing in this problem. So it's really a key problem here, but let's see how it works out. If y of x is given to us, this sort of generic power series, that's the guess we'll make to solve differential equations in the next lecture, then y prime of x, well, we're going to take the derivative there, n equals 0 to infinity, of, now, I'll put an a sub n because that's a constant, but the derivative of x to the n is n times x to the n minus 1. And so we get this new series, but you notice that the n equals 0 term is 0, and that's because of this factor of n right here. So that n equals 0 term of that series really doesn't change anything. So in fact, I can leave that off and just start the series at n equals 1. So we can omit that n equals 0 term. And so I can rewrite this series, the exact same thing except for n equals 1. And that's because instead of adding up the n equals 0, 1, 2, 3 terms, I notice that the n equals 0 term really isn't doing anything, so I can just add up the n equals 1, 2, 3, 4 terms. So I'm writing the same thing here, an x to the n minus 1. And I wanted to, it says something about shifting the indices of summation so that they start at n equals 0. I want to show you what I mean by that. If I expand out this series, I'm going to start out with n equals 1, and I'll get a sub 1. X to the 0 is just 1, so I won't put anything there. Plus, when n equals, so that was from n equals 1 term. The n equals 2 term gives me 2a sub 2 times x to the 1. N equals 3 term gives me 3a3 times x squared, and so on. And now I'm going to sort of forget the old version of the sigma form and just look at these terms. And if I want to write it in sigma form now, and I want to write it so that there's an x to the n there, what I notice is that these coefficients, these numbers on the coefficients, are one higher than the power of x. So here I've got 3a sub 3 x squared. So the coefficients are one power lower. So what I'm going to do is I'm going to put n plus 1. I think I didn't leave myself quite enough space here. Let me rewrite that. N plus 1, a sub n plus 1, x to the n. And if I do that, that'll make sense if I start at n equals 0. Because if you think about that, if I plug in n equals 0 here, I'll get 1 times a2, or sorry, 1 times a1 times x to the 0, which would give me just exactly n equals the a1 term here. The n equals 1 term would give me 2a2x. The n equals 2 term would give me 3a3x squared. And so I'm going to end up getting the exact same series that I wrote above. I'm just using a different index of notation to keep track of that. And let's look at what effectively happened here from when I expanded it out and wrote it in a new form. If you look at this n equals 1 term, the index went down by 1. So we lowered the index by 1 because it went down from 1 to 0. And then all the n's in the formula, all these n's got raised by 1. So that n turned into an n plus 1. The n in the subscript turned into an n plus 1. And the n minus 1 turned into an n. So to fix that, you raise the n's in the formula by 1. So that's going to be a really, really useful trick for us to use in the differential equations lecture next time. So you really want to keep this in mind. If you lower the indices by 1, then you raise the n's in the formula by 1. And it works the other way too. If you raise the indices by 1, then you lower the n's in the formula by 1. And it's sort of a way of adjusting the powers so that we can make different series be compatible with each other. So let's practice that by going one more step here by finding y double prime of x. So y double prime of x, that's the second derivative. Again, I'll start with n equals 0 to infinity. Now, I've got an x to the n minus 1. Well, I still have n. X to the n minus 1, if I take its derivative, will give me n minus 1. There's still an a sub n. X to the n minus 2. That's by taking the derivative of this expression right here. And then I notice, again, that the n equals 0 term, because of this n right here, will be 0. And the n equals 1 term, let me write that down, the n equals 0 term is 0. And because of that n minus 1, the n equals 1 term is also 0. So I can drop those two terms out and just start it at n equals 2. N equals 2 to infinity of n times n minus 1 times a sub n, x to the n minus 2. I'm not shifting the indices of summation yet. I'm just dropping off the first couple terms because I noticed that they're going to be 0. So I'm not doing this business over here where I'm shifting the indices. That's what I'm going to do next. So now I look at this and I see that that x to the n minus 2 right there, I want to raise that up and make it x to the n. So what I'm going to do is I'm going to raise the n's in the formula by 2 in order to get that n minus 2 up to an n. And to make that work, I have to lower the index by 2. By the same principle. I won't bother writing out the series this time. It's the same principle as before. So that n equals 2 in the index, I'm going to drop that down to n equals 0. And I'm going to raise all of these n's by 2. So I'll have n turns into n plus 2, n minus 1, raise it by 2, get to n plus 1. A sub n becomes a sub n plus 2. X to the n minus 2 becomes x to the n. So let me box what I've figured out here. Y prime is n equals 0 to infinity of x to of n plus 1, a n plus 1 x to the n. Y double prime is n equals 0 to infinity, n plus 2 times n plus 1 times a n plus 2 times x to the n. These are really important formulas. It's worth studying them very carefully and making sure you understand them or at least remember them, because we're going to be using them very heavily next time when we use series to solve differential equations. But let me recap how we obtain those formulas. We started with y prime of x. I took the derivative of this. So the derivative of x to the n is n x to the n minus 1. And then I noticed that the first term, that n, would just be 0 anyway, so I dropped it out. So I started at n equals 1 instead of n equals 0. I'm dropping off the n equals 0 term. And then I did this shifting index trick where I lowered that 1 down to 0, and then I raised all these n's. And the way you can justify that if you want to is to kind of expand out both this series and that series. And if you expand out either one, you'll see that you'll get this series either way. Those are really the same thing. So that was my formula for y prime. For y double prime, I went ahead and took another derivative of x to the n minus 1, and I got n minus 1 x to the n minus 2. I noticed that since I have an n and an n minus 1, the n equals 0 and the n equals 1 term are both going to be 0. So I dropped those out, and so I can start my index at n equals 2. That was not shifting the index yet. That was just dropping off a couple 0 terms. And then I'm going to use this same principle where I lower the index by 2, so that's why that 2 became a 0, and then I raise each of these n's by 2. So that n became n plus 2, that n minus 1 became n plus 1, that little n became an n plus 2, and that n minus 2 became an n. And again, if you sort of don't trust that, if that seems like magic, just expand out each one of these series. Expand out this one and expand out this one. Write out the first few terms of each one, and you'll see that you get the same series either way. So this is going to be absolutely crucial for us when we use differential equations to solve, or when we use series to solve differential equations. That's the topic of the next lecture, and that concludes our review of power series for this lecture. So you've been watching the differential equations lectures on Educator.com. My name is Will Murray. Thanks for watching.